Okay, welcome to this second Poster Blitz session of the fNIRS 2022 virtual part of the conference. For maybe some of you already were present in the last Poster Blitz and virtual session yesterday, but I would like you to explain again how you can ask questions to speakers. So today is a Poster Blitz session, which means that you can't ask question live. So we won't have time to ask question live and ask live replies. But what we invite you to do is to go, let me share my screen. So to go to the virtual program conference webpage that I will share in the chat later on, and then you can go to Poster Blitz session 2, which is here on October 5th, and then for each abstract you can select the abstract, and then you will see a chat here where you can write your question and then post a comment to the question, and then the comments will be displayed here below, as you can see, for example, here, and the speaker, the author of the abstract, can reply to you. So we invite you to post as many questions as you want to the speakers and continue your discussion offline. Another recommendation is if you can please write your English name when you join in to the webinar, or rename yourself if you already joined with a different name, please, so that we can track the attendees. So the chat is enabled here, but we invite you not to ask questions in the Zoom chat and use that just for any technical problems you might encounter during this webinar presentation. Okay, so after this general instruction, I will hand over the floor to today's session chair, Hubin Zhao and Samuel Montero Hernandez.
Okay, hello everyone. My name is Samuel Montero. I'm a postdoctoral fellow in the University of Houston, and I will be one of the chairs today with Hubin Zhao.
Yep. Hello everyone. My name is Hubin Zhao, currently assistant professor at University College London, and it's really my great pleasure to work with Sam, Sabrina, and other colleagues for today's session.
Okay, well, welcome to the third day of the virtual modality of the 2022 fNIRS conference. And today we'll having the second session of the Poster Blitz, which consists of a 3-minute presentation. And let me share my screen so you can see. Share screen. Okay. Okay, our first speaker today is Xiyuan Yang, and
hello.
I'm giving you.
Hello, sorry, do you mind switching to the PowerPoint version of my slides, please?
Yeah, this is the PowerPoint version.
Oh, good, that's good. Okay, I can control your screen now.
Okay, yeah, you give me a sec. Okay, you should be able to control the screen.
Right, thank you. Shall I start?
Please.
Right. Hello, I'm Zhiyuan from UCL. I'm happy to kick off the day with my presentation. You are welcome to find the abstract on this webpage or simply scan the barcode. So this study aims to, sorry, I'm clicking, but it doesn't move. Wait, right. Good. So this study aims to employ a customized miniature broadband fNIRS system to examine neurovascular and neurometabolic coupling of an animal model of cerebral small vessel disease, the spontaneously hypertensive stroke-prone rat, and then to explore the protective value of a potential therapy in nimodipine on vascular function. This panel here shows the overall experimental design. The animals were randomly allocated to either placebo or nimodipine diet, which lasted for 3 months. Broadband fNIRS recordings were acquired before diet when the rats were young, and after diet when the rats got old. The broadband fNIRS instrument involved in the study was previously described in this publication. The optos were placed non-invasively on the somatosensory cortical region of anesthetized rat upon shaving the head. The advantage of this instrument is that it can measure mitochondrial oxidized cytochrome C oxidase, which is an enzyme in the mitochondria closely involved in aerobic respiration. So therefore, the cytochrome C oxidase is a marker for metabolism. So upon stimulation, we can get our recordings. As we can see here, during stimulation, there is an increase in oxyhemoglobin shown in red, a decrease in deoxyhemoglobin shown in blue, and an increase in mitochondrial oxidized cytochrome C oxidase here shown in green. We also calculated HbDIF as blood oxygenation and HbT as blood volume. So here we got a reproducible response upon stimulation. So we took the average of the first 4 responses shown here and got the averaged curves. And then we quantified the averaged curves to get response amplitudes. The higher the better, and peak latency, the shorter the better. So we can see here that, for example, this graph, the placebo group here had the longest latency of around 14 seconds, but nimodipine group had shorter latency of around 11 seconds. However, the shortest latency of around 9 seconds occurred when the rats were young. This goes the same for all the neurovascular coupling and neurometabolic coupling parameters. So taken together, nimodipine alleviated the decline in neurovascular coupling and neurometabolic coupling caused by disease progression. In conclusion, broadband fNIRS instruments are able to detect deficits in neurovascular and neurometabolic coupling. Also, nimodipine is revealed as an effective therapy to protect from vascular deficits. So our findings provide insight into clinical management and clinical monitoring and management of cerebral small vessel disease. Yeah, that's the end of my talk. I will be with my poster today and on Friday. So happy to see you at the Gather Town event.
Thank you. Thank you so much, BD.
Thank you.
Okay, our next presenter.
I'm still controlling your screen.
Oh, okay. Okay, now it should be fine.
Fine.
Okay, our next presentation is from the University, Purdue University. It's Vidya Vijayakrisana, and please let me.
So I don't think I can control the screen.
You should be able now.
Okay, yeah, I'm good. So can I start?
Yes, please.
Hello, everyone. I'm Vidya Vijayakrishan Nair from the Weldon School of Biomedical Engineering at Purdue University. So today I'll be talking about the coupling of peripheral and cerebral hemodynamics during wake and sleep states. So first of all, hemodynamic low-frequency oscillations in the frequency range of 0.01 to 0.1 Hertz are widely detected in functional imaging studies, including fNIRS and fMRI. So as stated in the title, the purpose of the study was to investigate the periphery to brain hemodynamic coupling, particularly in this low frequency range across the wake and sleep states. So the natural question here would be why this is important. So prior studies have actually shown that the peripheral hemodynamic oscillations measured using fNIRS actually represent the non-neuronal systemic physiology and are also strongly coupled with the cerebral hemodynamic LFOs, that is low frequency oscillations, with varying time delays during resting state wakefulness. However, we know that the neuronal as well as the physiological processes vary during sleep, and therefore it is possible that this periphery to brain coupling may also vary across the wake and sleep states. So in order to investigate this, we conducted a concurrent EEG, fMRI, fNIRS study with 8 healthy volunteers, wherein we recorded the low-frequency hemodynamic oscillations simultaneously at the peripheral sites using fNIRS, that is the 4th fingertips of both arms, as shown in the figure, and centrally in the brain by using both fMRI. In addition, we also simultaneously recorded the 32-channel EEG for sleep scoring. So now moving on to the results. So essentially, we calculated the cross correlations of the hemodynamics collected from the fingertips, which is the green trace, representing the change in concentration of oxyhemoglobin from fNIRS, and then in the brain, which is the red traced by bold fMRI, in continuous 5-minute segments of wakefulness and non-rapid eye movement sleep stages 1 and 2 for every participant. So as you can see from the results of a representative participant here, the results illustrate that the hemodynamic LFOs from the periphery and the brain are strongly correlated with each other with varying time delays across all the 3 different measured states. So what does this strong and consistent periphery to brain hemodynamic coupling in this particular low frequency range across both of the wake and sleep states actually indicate? So it means that the effects of non-neuronal systemic circulatory physiology on brain hemodynamics do not actually alter significantly during light NREM sleep as compared to resting state wakefulness, and also that this particular non-neuronal systemic physiological component that travels with blood continues to remain a major source of brain hemodynamics during sleep as well. So that's all about the study for today's talk. Thank you all, and I'll be happy to answer any questions that you might have during the virtual session today or in person at Boston. Yeah, thank you.
All right, just in time. Thank you, Vidya. Let me change a little bit this thing. And oops. Okay. Our next presentation is okay, modulation of language-related networks during movie viewing using whole head NIRS, and is going to be presented by Isabel Nicholson. Okay. Isabel, you should be able to see the remote now. You can start.
Okay, thank you. Hello, everyone. I would like to start off first by thanking my co-authors, Sarah Sanchez-Alonso and Richard Aslan. Today, I will be presenting our research on the modulation of language-related networks using data that we collected during a movie watching paradigm with a whole head NIRS montage. So we ran our paradigm on 42 adult participants, all between the ages of 18 and 35, and all of whom spoke English as their native language. So we additionally screened for fluency in Spanish. As you can see, our paradigm consisted of a movie watching task using clips from the children's movie Despicable Me. So the movie clips were presented in 3 different audios. So an English audio, or our native language condition, a Spanish audio, or our non-native and non-fluent language condition. Again, as I said, we screened for fluency in Spanish, and a distorted audio, or time-reversed English speech, with base phonemes and pros preserved, but rendered overall unintelligible. So all participants watched the same movie segments in the same order, but the audio condition that each clip was presented in was counterbalanced across participants. Additionally, we incorporated short channels into our whole head NIRS montage for more precise regression of extracerebral noise. Anatomical co-registration was also performed using a light structure 3D scanner that allowed us to more precisely map optode locations onto the underlying cortical tissue. So today I will be presenting data from our English and Spanish audio conditions. So data analysis from our distorted audio conditions is currently ongoing. So first, when we compute the brainwide activation differences between the English and Spanish audio conditions, we see that the native language or English condition is correlated with increased activation in the left prefrontal cortex and left superior and middle temporal gyri at statistically significant levels. We also observe increased activation in canonical speech processing areas, i.e. left Broca's area and left supramarginal gyrus or Wernicke's area at both the group and the subject level. Next, we also did various functional connectivity analyses, and when we examined subject connectivity using this English over Spanish contrast, we continue to see that English speakers display functional connectivity patterns that are significantly different when processing their native language, again, English, over a language that they do not speak. So this first figure shows seed-based functional connectivity for our English over Spanish contrast. Our seed region here is 3 channels in the left supramarginal gyrus, again, Wernicke's area, based on the ROIs that you see displayed to the left, as well as replicability in each individual subject's image reconstruction. It is denoted on the image with the white diamond. And to look at full head functional connectivity, we computed the group results for the English audio and Spanish audio conditions. We then subtracted the Spanish correlation values from the English and isolated the residuals of the channels with the greatest flux. So the black lines represent the top 20% of condition-to-condition channel increases, while the red lines represent the top 5%. And as you can see, the native English condition is associated with increased intraparietal and temporal occipital connectivity. So thank you for your time. I'm presenting on GatherTown today and also at Poster Session 1 on Monday. Please come say hi.
All right, thank you, Isabel. We have to move to the next presentation. Okay, the next presentation is high-density multi-distance fNIRS for improved detection of frontotemporal activation during verbal fluency task, and is going to be presented by Jessica. Jessica Anderson. Yeah. Jessica, you should.
Yes. Yes, I think I'm controlling the screen now. Thank you, Sam. So
Okay.
I'm Jessie Anderson with Boston University, like he said, researching high-density multi-distance fNIRS for improved detection of frontotemporal activation using verbal fluency task, or VFT for short. VFT is commonly used with fNIRS to investigate psychiatric disorders. And the consensus in literature is that functional activation in the frontotemporal region is reduced in patients as compared to healthy controls. The potential of this system paradigm pairing in psychiatric health research goes beyond the advantages of fNIRS over other neuroimaging modalities. When we consider the requirements of standard of care for psychiatric health assessment, including certified personnel, language, and culturally appropriate questionnaires, a lack of stigma, we see that these requirements can render equivalent and appropriate mental health care largely inaccessible in low resource settings. So the fNIRS VFT pairing therefore also has great potential to bring objective, conversation independent assistance to the process for improvement across all contexts. Presently, most of the studies using fNIRS VFT use a standard 30 millimeter grid pattern array of optodes over the frontal and temporal regions. Unfortunately, this design suffers a lack of spatial specificity and poor signal reproducibility. To address this, we have designed a here we go. We have designed a hexagonal in the bottom left portion of the slide here, a hexagonal multi-distance high-density optode array across the frontal and temporal regions, and we are comparing its detection of VFT-induced activation in healthy adult subjects to that of a traditional sparse array in the top left. For a given session, as shown on the right, subjects wear one of the caps and perform a resting task, then phonemic VFT. The cap is then switched out and tasks are repeated with the different letters. Performing a Monte Carlo simulation and image reconstruction in an atlas viewer, we see on the left, compared to the sparse array in the top row, the high density array on the bottom yields dramatic increase in sensitivity, decrease in localization error, and also noticeable improvement in resolution. On the right, I'm displaying results from a single subject. For each channel in both arrays, we display on the top time series HRF, and on the bottom, color scaling by t-value from pairwise t-test, with deep red channels indicating the most significant HBO increase. So this data meets sanity checks that 1, we are detecting HRF across the frontotemporal region as expected, and 2, as emphasized by the circles, for a given subject, both arrays detect significant functional activation focused in some of the same regions. So moving forward, we'll expand analysis between arrays on the subject level and then at the group level as we recruit a goal of 15 subjects. And after a month's time, each subject will return for a second session in order to assess repeatability. This ongoing effort provides foundational work in research in high-density fNIRS and may also lay groundwork for improving future studies probing psychiatric disorders with fNIRS and VFT with application for global mental health. I'll be at my poster in Gathertown tomorrow at, I believe, 9 a.m. Eastern, and in the poster session 2 next Tuesday. Thank you.
Thank you, Jessica. Thank you. We have to move to the next presentation. Oh, thank you. And the next presentation is titled Towards a Fully Integrated Smart Textile Patch-Based Cap for Multi-Distance CW-fNIRS Whole Head Imaging, and is going to be presented by Christian Barkowski.
Hi, everyone. Yes, welcome. Thanks for attending to the Poster Blitz session. And yeah, my poster or my work here is mainly about hardware design. And what we did is basically we took our, let's see, next slide. Sorry, no, it works. We took our well-established standard for full head montage and transferred the setting to the smart textile world. What is a smart textile? Smart textiles are fabrics equipped with electronics to serve as sensors or reactors. And what we did, we took our bundle-based, opto-bundle-based setup, took the electronics, sensors and detectors, and embedded them in such fabric patches as you can see here on the right side. Each patch has 8 detectors, 8 sources, and additional 8 short channel detectors. And they feature such a brush-like front end, as you can see here. Every optode is spring-loaded. That means we do have, although we have a kind of a fixed structure, we do have a certain flexibility. Additionally, as a second feature or flexibility feature, we do have those flexible holders in this cap we implemented. So there's an extra way to wiggle this whole setup through the hair. All in all, as you can see, as a major difference, we, as we embedded all the electronics into the SMECTAT patch, we have improved compactness and usability, as there are just 12 cables left on the cap, whereas the gold standard has more than 120 loose cables in it. We reduced the total weight by 300 grams and the total height by 20%. We tested this whole setup internally on 8 subjects with different head sizes, head shapes, and hairstyles. And the long channels have very promising or excellent results. So we did some contact tests or contact evaluation with the Aurora software from fNIRS, and signal quality was done via the fNIRS MATLAB script based on a 6-minute resting stimulus. And on BART subjects, as you can see, we do have a very homogeneous quality level, and for short and long distance channels. And for long-haired subjects, you see some gaps in this graphic bar graph here. Those are mainly caused by this short channels, as these are not spring-loaded actually, and therefore they do have some issues to penetrate the hair properly. But this can be fixed by adjusting the carrier cap and doing some additional iterations with the whole design. Thanks a lot. I'll be on my poster today in roughly an hour, and see you with some of you in Boston. Thanks a lot for your time.
Thank you, Christian. Okay, have to stop the remote control. And our next presenter, oops, yes. Our next work is the role of theory of mind in children's lion behavior, a functional near-infrared spectroscopy study, and is going to be presented by Xiao Pang.
Yeah, correct. Yeah.
Okay.
Thank you very much. Okay, I can control. So, okay, thank you very much. I'm presenting this paper on behalf of Liang Yibiao because he has class. So our question is whether children's lying is linked with serial mind. So serial mind is very commonly studied in developmental psychology. It means how children can understand others' minds. So to tell a lie, children need to understand about that the other people does not know about the truth, so that they can instill the false belief into others' minds. There's a lot of behavioral studies have investigated these questions, but none of them try to investigate this using neuroimage studies. So it is the very first study we try to look at whether children tell lies, and there will be a serial mind network involved. So we studied these questions with 3 to 6 year old children, and we recruited 60 typically developing children, and they are 3 to 6 year old, and they are all boys. Yeah, so we basically play the games with the children, and we have 2 conditions. One is the experimental condition, and the other is the control condition. In the experimental condition, we tell the children, this is a very bad, mean puppet. You have to tell lies to them. But in the control condition, we tell them, the puppet is nice, then you have to tell the truth to them. So we know that children, can you, can you go up? Yeah, some of the children are very cannot tell lies because they haven't developed their mature serial mind yet. So that our this design, we can create 3 responses. One is lying condition, lying response. The other is the telling truth response, and the third type is a control response. So with this a response, we also tested the children's behavioral serial mind task. So we select the RTPG as our research of ROI for the serial mind network. So our results show that most of the children can tell the lies, and there's no significant difference between the network between lying and the truth telling, but there's interactions between serial mind network and whether telling truth and telling lies. So the interesting is when children's serial mind ability become better, then they have less activations in the serial mind network. This means children automatically learn how to tell lies, and so that there will be a less serial mind network involved to tell the lies. Thank you very much.
Thank you, Xiao. Excellent, just in time. Okay, our next work. Yes. Our next work is using fNIRS to investigate the neural correlates of distraction in 8-month-old infants. It's going to be presented by Giulia Serino from University of London. And I think, Giulia, you need the PowerPoint presentation, right?
Yes, exactly. Thank you.
Okay. Let me change to that.
This is not PowerPoint.
Yeah, okay, sorry about that. Okay. All right. You're good to go.
Okay, thank you. All right, for the next 3 minutes, I will speak about attention and distraction development in babies. So if you are in the crowd and someone says your name, they will probably get your attention, right? But if they say someone else's name, they probably won't. And even if the 2 names are very similar at a physical level, the difference is that one is relevant and one is not for you. And so it seems that there is a set of frontal and parietal regions in the brain, which is more sensitive to the behavioral relevance rather than the saliency of stimuli outside the current focus of attention. And so we wonder whether the same network is already tuned to relevant information from early on in life. And to answer this question, we use a combination of eye tracking and fNIRS methods. And specifically for the fNIRS, we use 224-channel baby bright NIRS system for Martinis with a custom design array covering the frontal and temporoparietal regions bilaterally. So what we did. First, we exposed babies to two shapes while recording the eye movements. One shape paired with a social reward and one shape without a reward. So, for instance, in this example, they saw the green circle followed by nothing, and then the orange triangle followed by my face, which is meant to be the reward. And then after 10 trials, we presented babies with both shapes, and the preliminary results show that they look longer at the shape that was previously associated with the reward. So this is great. It means that baby learned the cue reward association, but then our question was, can babies actually use this information to reorient their attention while they are engaged in something else? So what we did, we show babies this video of a cartoon animal dancing. And while they were watching the video, the two shapes pop out in the periphery of the screen as distractors. And in the meantime, we recorded their brain activity and their eye movements. And so these are the preliminary results. And here we have changes in oxy and deoxy after preprocessing. And this is the mean hemodynamic response function from 7 babies. And in line with our hypothesis, the frontal region show a greater sensitivity to the informative, so the solid line, rather the uninformative distractors. And this is similar with other studies, but differently from other studies, the same response was not observed in the temporoparietal regions. And at a behavioral level, the eye tracking data suggests that baby can indeed use the information they learn to orient their attention. Indeed, the preliminary data show a trend of faster eye movements to orient the attention from the central video to the informative distractor, and overall babies look longer at the informative than the uninformative distractors. And that's it. If you have any question, I'm in Gathertown today and in Boston on Friday, 11th of October. Thank you.
Thank you, Julia. Before proceeding to our next presentation, just a brief reminder to our presenters that you will see a small lag while you are controlling the slides. So please keep it in mind. We have to move to the other file. All right. Next with us, we have the poster characterization and detection of intracranial pressure alteration and by hybrid diffuse optics in benign external hydrocephalus children, and is going to be presented by Susanna Tagliabue. Susanna, you should receive the notification of the control.
Not yet. Okay, should be. Okay, should be working. Okay, so benign external hydrocephalus in infants is caused by a dysfunction in the drainage of the cerebrospinal fluid, the CSF, although this condition generally doesn't require any treatment. However, recent studies speckled some evidence of morbidity, such as developmental delays. BE was also associated with the presence of some pathological alterations of the intracranial pressure, ICP, within the low frequency range and with some specific patterns, where here we see one on the right from the literature. And so taking all of this together, we designed the study in order to find some information about the oxygenation, hemodynamics, add some biomarkers, and eventually be able to see these ICP alteration, these waves, by non-invasive methods. And therefore, we saw that there could be a role played by hybrid diffuse optics. For this reason, we set some hypotheses, but due to time constraints, I will only hybrid diffuse optic signal show some alterations at the same time as these intracranial pressure changes. And the approach that we follow to answer this hypothesis is the following. First, an expert doctor identified on the intracranial pressure some pattern by visual inspection. Later, a colleague of mine carried out the same type of analysis in a blinded way to identify these same patterns on the blood flow index, the BFI. And afterwards, in order to compare them, we assessed the sensitivity, which basically tells us how many times out of the total we actually caught a wave, an alteration, and the specificity, which tells us how many times we didn't get a wave when it was not there. So thanks to our collaboration with Valdebron Hospital, we managed to recruit 11 children for nocturnal measurements for 2 consecutive nights. And hybrid diffuse optics measurement was carried out on the frontal lobes. Meanwhile, we were also recording invasive intracranial pressure. And here we see an example from one nocturnal measurement. On the first row, we see the ICP here on top, where the doctor identifies these patterns. And the second row, we see the blood flow index, where my colleague also identified the same patterns. And then we compared them in order to identify the true positive, true negatives. We did this for all of the measurements, a specificity of 76% and a sensitivity of 90%, which are quite promising numbers that prompted some more advanced analysis, which I would be happy to share with you during my poster session. So hopefully in the future, invasive monitoring could replace the invasive one. Thank you.
Thank you, Susanna. Thank you so much. Okay.
Please.
Okay. Our next work is titled.
Yeah, I can, I can call it. Okay.
Please remember to mute yourself if you are not going to be a presenter.
I am.
Yeah. Sorry about it. Our next work is concurrent associations between parent-infant interactions and cortical selectivity to social, auditory, and visual stimuli in 5-month-old infants, and is going to be presented by Diana Ilka from University of Cambridge. And Diana, you should receive the remote notification now.
Thank you. So my name is Diana, and I would like to present to you, go straight into action and sort of tell you what I was studying. So from the very birth, infants show selective responses to social stimuli, auditory and visual, when compared to non-social stimuli. And these responses seem to be changing with age, with infants becoming more and more specialized to process social versus non-social stimuli. And in some populations, like those infants with autism, the social selective responses are shown to be reduced as early as 5 to 6 months of age. So given this developmental trajectory and the nature of these responses, in this study, I really wanted to investigate and better understand the context in which the social brain development takes place. So in my study, I coded the behaviors of infants and parents from parent-infant interactions. And I essentially asked very simple questions, and whether those babies who show reduced socially selective responses to socially, auditory, and visual stimuli also experience less social interactions with their caregivers when compared to infants who showed increased social responses. I'm sorry. Okay. And given the previous literature, I expected that the positive associations, meaning that those babies who would show increased selective social responses to social stimuli, both auditory and visual ones, would also be the ones who experience more social interactions with their caregivers. But very intriguingly, the findings actually showed the very opposite direction. So here I'm presenting just one of the graphs of what I was measuring, and I measured the dyadic engagement between the parent and the infant, and I actually showed that the more engaged they were with each other, the less socially selective responses they experienced to social auditory stimuli, and that was also the case for the social visual one. And moreover, these findings have been replicated across two different studies, so two independent studies. And I'm currently, and also one of the students from the University of Cambridge worked on a third independent data set who also showed the same response in the same direction. So, sorry, it takes time to move. Yeah. So I would be very inviting you all to my poster to discuss these very intriguing findings and discuss with me what they mean. And my poster will be also physically hung by my colleague Borja during the fNIRS conference on the 12th of October. But I'm also very willing to discuss it with you today and tomorrow, basically after this Poster Blitz, and also tomorrow around the same time, to discuss these findings and your thoughts and ideas about this. And of course, please message and email me, or you can comment it if you have any additional questions or ideas. Thank you.
Thank you, Diana. Thank you so much.
Yeah.
Oops. I need to recover the control. Okay, sorry about that. Our next study, our next poster is titled A Comparative Study on the Global Topological Properties of the Human Brain at Rest with Simultaneous fMRI and fNIRS, and is going to be presented by Victor Sanchez. Victor, you should be seeing the remote prompt now.
Hi, Samuel.
Yes, you can start, please.
Okay. Hi, everyone. My name is Victor Sanchez. I am a PhD student at University of Campinas in Brazil. Today, I present to you a little about how we use graph theory to make cross-validation between two neuroimaging techniques. It is interesting once resonance-state functional connectivity reveals a brain interaction that can be quantified through graphs. In this sense, the question we aim to respond is how do the topological properties vary with the neuroimaging technique? To respond it, we perform simultaneous fMRI and fNIRS measures at rest in 34 participants and 5 rounds per participant. We build time series for all contacts, and we use the Pearson correlation to estimate the resting state functional connectivity. Then, for the analysis, we estimate the global topological properties and explore the intersubject and intrasubject variability. In the step 1, for checking the group analysis, we compute the z-values with the Fisher transformation. Then the group average was obtained by averaging the matrix across all rounds and all subjects. And also, we estimate the z-score. The main topological parameters are degree, standard deviation, between centrality, clustering coefficient, and efficiency. They were all estimated using Winding and Winding graph. And this was made for H technique contrast. Now, regarding our results, we didn't find any statistical difference for resting state functional connectivity graph. However, fNIRS slightly yield a denser graph than both fMRI. In the end, we estimate the intersubject and intrasubject variability across all subjects and all rounds. And to do that, we use the normalized geodesic distance, in which a coefficient near to 0 means that the matrices are very similar. Which brings us to the conclusion that our studies show that PCA-corrected fNIRS data yield resting state functional connectivity graphs that have similar topological properties and be more reproducible than Boolean fMRI. Please, for more details, visit my poster. Thanks to financial agency support, and thank you for your attention.
All right. Thank you, Victor. Thank you so much. Okay. And our next work is titled fNIRS Flexible MATLAB Toolbox for fNIRS Data Analysis, and it's going to be presented by Julie Tremblay from University of Montreal.
Good morning. It's a pleasure to present you the fNIRS Toolbox this morning. I'm working at the Lion Lab in St. Justin Pediatric Hospital as a biomedical engineer, and we are using near-infrared spectroscopy on many research projects, mostly related to children development. This population, as many of you know, it's challenging to test depending on the cooperation of the children, and the artifact it's an issue, and it's important to be really aware of how you're dealing with artifact with this population. So the aim of this toolbox was to give us flexibility in our data analysis, and we are happy to share it with the community. fNIRS, it's an open source toolbox. Oh, sorry. Small delay. fNIRS, it's an open source toolbox built in MATLAB to give us a visual support at any step of the analysis. It contains several functions to perform artifact detection and data decomposition, such as target PCA, parafac, and GLM. The artifact rejection approach is semi-automatic, so it's always be possible for the user to review and adjust the rejection if necessary. This validation helps to ensure the data quality. The toolbox function are implemented in SPM batch, a tool largely used in neuroscience field to perform fMRI analysis. The advantage to do so was to have the flexibility and the efficiency to run a custom pipeline easily on the data. It's also allowed to synchronize additional measures such as EEG or physiological data or video when they were recorded simultaneously with fNIRS. fNIRS could be used to perform part of the analysis such as artifact detection or correction, or to do more complete analysis to explore the hemodynamic response or functional connectivity network. A strength of this toolbox is the flexibility to supervise the step by visual inspection, and it do not require programming knowledge. You can come to visit us at the virtual poster session. Our paper were recently accepted in the Journal of Neuroscience Method. It's a good introduction if you're interested to use the toolbox. It's also available on the GitHub platform. You can find tutorial and example of data on the wiki. I like to thank the whole team who contribute to this project, and I hope that we have the opportunity to continue to improve it for further needs and research questions. So thank you for your attention.
Thank you. Nice. Thank you, Julie. Okay. And we are approaching to the end of this session. Our next poster is the neural correlates of metaphor and fNIRS study, and is going to be presented by Anna Schwartz from Northeastern University.
Hello. We use metaphors and literal sentences every day, and metaphors are a really important mechanism to allow us to communicate about ideas that aren't already embedded in our language. So we wanted to look at the neural correlates of metaphor processing as compared to literal phrases. So metaphors in research have a specific definition that differs from the literary term, metaphors in research are phrases in which two constructs are compared to highlight how one construct's meaning overlaps with the other construct's meaning. So when you look at the metaphorical phrase in the example below, his memoirs were a toilet flush, we understand that something about the memoirs is not ideal and maybe they should be thrown away. So not a lot of research has been done on metaphors, on the neural correlates of metaphors, and most of it has been done using functional MRI. So there's a debate that continues as a result of the fMRI research around the extent to which the left hemisphere, sort of traditional language centers, versus right hemisphere is necessary in the processing of metaphor. And we were looking at some of the literature that suggested that it may be the difficulty level that's causing this debate, where the right hemisphere might be being pulled in for more difficult items, where metaphors are more difficult than literal phrases, but also novel metaphors that have never been heard before are more difficult than metaphors that are familiar. So we thought that there would be some benefit to replication of some of these studies with fNIRS, and we wanted to look at this difficulty level difference especially. So we wanted to look at the hypotheses that metaphors are more challenging to process than literal phrases and require more resources, and also that novel metaphors are more challenging to process than familiar metaphors. Just waiting for slide to advance. No.
Please try again. I just received the notification that you are controlling the screen. Oh, you should click on the presentation first. Okay. There you go.
So we had 18 participants, and all of the participants saw half of the phrases before they were put into the fNIRS cap. So they were made familiar with some of the phrases, and some of the phrases that they saw were novel. And then we counterbalanced across 4 conditions where there were familiar metaphorical phrases, familiar literal phrases, and then the same for novel phrases for both conditions as well. And our results, our findings are that the activity for the contrast of both metaphor over literal sentences and for novel metaphors over familiar metaphors were both left lateralized, except for some temporal regions. And these results sort of align with our hypotheses and the results that we saw in the research from Cardillo in 2012, with some differences. And you should come to our poster to find out more. It is on October 12th at noon, and I look forward to seeing you there.
Right. Thank you, Anna. And well, thank you so much, all the speakers, and that concludes today's presentation, today's session. Thank you also to all the attendees, and as a reminder, don't forget to join GatherTown today after this session, so you can virtually visit the posters or meet the speakers. And finally, we would like to invite you to join us tomorrow for the next Poster Blitz session, which is the session number 3 at 8 a.m. Boston time. And thank you, everyone.
Thanks to Sam. Perfect timing. Thanks to everyone. Thank you. Have a nice day. Enjoy the rest of fNIRS virtual and in-person conference.